In this next series of videos, we're going to be talking about circles. Surprisingly, circles are going to have more properties in them than we have seen in any of the other shapes that we have studied. And I find that kind of interesting because overall, the definition that we have for a circle is very simple and the shape that we have is very simple. Okay, by definition, a circle is a set of all the points that are equidistant from a common point called the center. That common point is located here. This is the center of the circle. The curved part that is drawn here is the actual circle, not to be mistaken with all the space that would be inside of it. The actual curve is the circle, because along that curve, we have an infinite number of points that are all equidistant from that point. Okay, so we have some chosen measurement, which we refer to as a radius, that measures the distance from this point out. You could then plot a point there. You can measure out in a different direction, plot a point there, measure to a different direction, plot a point there. And if you do that an infinite number of times, the dots start to create the shape that we know as a circle. All right, for the purposes of the next part, we are going to be referring to this as circle O. Before we start looking at any of the properties that circles have, what we do need to go through is some vocabulary. And there is a good number of vocabulary terms that we're going to discuss. Right here you can see diameter, radii, and chord. We have a few others that I will be showing you in just a bit here. All right, so first let's draw a diameter with endpoints at D and M. Okay, a diameter is going to be a segment that goes completely across the figure, passing through the center. Okay, so we can literally draw that anywhere we want in the picture. I'm going to try and draw it so it doesn't actually go through my O. Okay, so this could be a diameter, and again, you could place it in all kinds of different locations. Okay, so we can call that DM, give it some endpoints there. Based on that, we can identify two different radii. Radii is just going to be the plural form for radius. Okay, a radius is going to measure from the center to the edge. So we have DO. We've also got MO. What I'm going to do is go ahead and put line segment symbols on top of those. Our third term here is going to be a chord. A chord is a line segment with endpoints on the circle. All right, so remember that the circle itself is the actual curve. So what we're going to do is identify 2 points along the edge of the curve and go ahead and connect them. We're going to draw a line segment CH such that it is a chord. All right, so let's just choose a couple random points. We'll call that C, we'll call that one H. Okay, and CH is going to represent a chord. It does have its endpoints on the edge of the circle. All right, notice that blank is also a chord. By definition, a diameter is also a chord. DM is a chord. It just happens to be the longest possible chord that you could have in a circle. All right, so I got a few more terms to identify. What we'll go ahead and do is read the definitions that go with them, then I'll move back up to the picture and show you what those look like. First, we have a secant. A secant is a line, segment, or array. Okay, so it comes in many forms here. A chord was just a line segment. Okay, so a secant is a line, it could be a segment, or it could be an array that intersects the circle twice and contains at least 1 point outside the circle. What we're going to end up doing is drawing ray SC. It will have to intersect the circle twice, and it will also need to go outside the circle. The next is going to be a tangent. A tangent is a line segment or array, sort of like a secant, that if extended intersects the circle only once. It only makes contact with the circle once. Even if it's infinite in its size, like a line or array, it will intersect the circle only once. And we're going to draw a tangent to circle O at T. Point T will then be referred to as a point of tangency. All right, so let's go ahead and draw a picture of a secant. The secant that we are going to be drawing is a ray SC. It does need to contact the circle twice, and it does need to extend outside of the circle. Since we do have a ray, what I'm going to go ahead and do is use point S as a point on the edge of the circle, and I'm going to go ahead and put that point right here. I'm just going to try and find a spot where I'm not going to cross other lines. Let's go ahead and also put C on the edge of the circle. Let's just put that there. It doesn't need to be, but I'm going to go ahead and put it there. All right, and then our ray, which is going to be called the secant here, can look like that. Okay, so in a way, it could look like a chord that's just extending out. That'd be okay. Now, this could also be a line, so it could go all the way through as well. Okay, the chords are going to be limited in their length. They have the endpoints on the edge of the circle. The secant is going to be passing through that circle. It's going to make contact twice. Next, let's go ahead and draw a line that is tangent to circle O. We do want it to be tangent at point T. Okay, so I'm going to identify a point out here that's just kind of convenient. Let that be point T, which is called a point of tangency once we draw our line. For the line to intersect the circle just once, what it is going to do is just bump up against the edge here. Just like that. A tangent does not have to be a line. It could be a ray or a segment, which means that it could have an endpoint at T and just extend that direction, or it could extend in this direction here. But if it were to extend forever, like the picture that we have here, it can only contact the circle once, which looks like this. It just sort of bumps up against the edge of the circle. As mentioned before, circles have many properties. In this video, I'm going to focus my attention on properties that are created using tangent lines. There's going to be two properties that we look at. The first, I'm going to take an inductive approach at. The second, I'm going to begin with an inductive approach, but then show you how it would be done deductively. To do this, I'm going to use patty paper. And I'm going to start with a picture of a circle. A good way to start any picture of a circle is with a center point. Okay, many times you're going to need to know where that is, so make sure that you mark that off first. All right, then based off of that point, I'm going to make a circle here. We're going to be investigating tangent properties, which means that I need to add a tangent line, and you can literally draw that anywhere you want. You could draw it here, you could draw it here, you could draw it here, whatever you decide on. Okay, so I'm going to go ahead and draw it in this spot, and that is a tangent line to the circle. What I want to do next is identify the point of tangency, or what I believe to be the point of tangency. It does appear that the circle overlaps the line a little bit, but it actually makes contact at a single point. Okay, so with my best judgment here, I'm going to go with that point. Okay, what I'm going to do next is fold the tangent onto itself. And when I do that, I'm looking for that point of tangency to be on the crease. Okay, so it looks pretty good here. See if I get that lined up good. All right, so a little bit of a pinch there. Well, I don't think I got that in the right spot. Okay, a little bit of a pinch. Then I'm going to make a crease. Okay, and you may notice, like when I fold it over here, the circle overlaps itself as well. Not just the tangent line, but the circle overlaps itself as well. And that point right there, which is the center, is along the crease. What that means is that this crease is going through the center of the circle and could represent a diameter or a radius. All right, but think about the fold that I made here. When I folded this over to match that up, made the crease right here, this wasn't any random crease that we had right there, okay? It may remind you a little bit of when we did perpendicular bisectors, except for the fact that I don't have endpoints that I'm matching up over here. Okay, so I don't get any bisecting of the line, because you can't bisect it, but I do get a perpendicular. I do get a perpendicular there. So the first property that we get from tangent lines is that the diameter and the tangent line will meet at a perpendicular at the point of tangency. Our second property is going to build a little bit off of that first one. All right, so a piece of patty paper. Let's go ahead and mark a center, make a circle. All right, and then what I'm going to do is identify a point that is outside of the circle. Let's make that point here. Okay, and then using that point, I'm going to draw two tangent lines. I'm going to draw one here, leaving that as an endpoint, and I'm going to draw one here. Okay, again, with that as an endpoint here. In addition to that, I'm going to identify the points of tangency, which I'm going to mark about here. I'll call that A. I'll call this one B. And that point that's out there, let's call that P. This is called point P. All right, in addition to that, I'm going to draw the radii that would extend from the center to the points of tangency. And what we had just learned from the other property is that you get right angles here. So we get right angles there. All right, now these as radii have the same length. They've got the same length. So I'm going to have those congruence markings. And I'm going to add in one more thing to the picture here, which is a segment going from P to the center. Okay, for that, I'm just going to use a dashed line now. Don't want to highlight that one too much. All right, and if we take a look at this picture, we end up with two triangles, essentially, right? We get two right triangles. We got the right angles. This would be a hypotenuse here. These would be leg lengths. These would also be leg lengths. And what's special about these two right triangles is that they're congruent to each other. And we can easily prove that they're congruent to each other. This is the deductive reasoning here. They both have the shared side here, which would actually be the hypotenuse of each of these. They both have that radii length, which would be a leg length, and they've got the right angles. So by hypotenuse leg shortcut, we can prove that these two triangles are congruent. And if they are congruent, then corresponding parts of congruent triangles are congruent, which would be BP and AP. BP is going to be congruent to AP by corresponding parts of congruent triangles. In other words, here's our property. If we have a point that is outside the circle, it is equidistant to the 2 points of tangency that you can create. Next, what we're going to do is talk about common tangents. A common tangent would be a tangent line that is tangent to 2 or more other circles. Okay, as we go through these different examples, I think it would be kind of fun for you to pause the video and see if you can think of what the picture would look like before I actually show it. To start things off, I'll go ahead and demonstrate the number of common tangents that you can get with two circles like this. Okay, so as a common tangent, what I could do is put a line across the top like this. Okay, so it's going to be tilted so that it makes contact with both of them. But it is going to be tangent to each of those circles, which makes it a common tangent. Okay, and if I can draw that segment, I could draw this one too. All right, so I got two common tangents shown, but there's actually a couple more that we can draw. You could draw one here. Okay, tangent to the bigger circle there, tangent to the little circle there. And you could go the other direction like this. All right, so given these two circles, you can actually draw 4 common tangents. Now, what would two circles look like to get exactly 3 common tangents? What would that picture look like? Okay, let's start with just one circle. All right, and then the trick to this is to figure out the placement of the other circle. Because if I put another circle here, I get that same picture. Whether it be a small circle or a big one, I can create the exact same picture there. All right, so maybe think of it this way. How could you take this picture of 2 circles and change it a little bit so that you get exactly 3 common tangents? The answer to that is to make the 2 circles themselves tangent. Okay, so you get the tangents across the bottom, across the top, And for the in-between, you can't tilt it without cutting through the circles, but you could just make it go straight through like that. And you get exactly 3. All right, so here's a few more that you could try out. How could you draw 2 circles to get exactly 2 common tangents? How could you draw 2 circles to get exactly 1 common tangent? And how could you draw 2 circles to get no common tangents? For 2 common tangents, what I'm going to do is look at the picture that we did for 3 common tangents. To get 3 common tangents, we needed to make the circles come together and make contact for that center part. Okay, now if those 2 circles come together even further, they begin to overlap each other, you will lose that common tangent that would be there. So for this picture, I'm going to draw 2 circles that overlap each other. You still get the common tangent on the bottom, the common tangent on the top, but you lose any common tangents that were in the middle. Okay, back at the very beginning, because the 2 circles were separated from each other, you got 2 common tangents in the middle. Once the circles themselves became tangent, you got 1 common tangent. As they come even closer together, they overlap each other, you lose that common tangent. You get down to 2. All right, so how could we move these even closer together to get exactly 1 common tangent? How could we do that? Let's take the other circle and start to move it all the way inside the other circle. But to do this, you are going to have circles that are different sizes. All right, so your common tangent is going to be located here. So we lose the top and the bottom common tangents, and now we're really just looking at that shared point that they have right there. All right, so 0. We could probably figure that one out now if you haven't before. Completely move the other circle inside with no contact. Impossible to get common tangents. Any tangent to the little circle is going to become a secant to the larger one, not a tangent. Any tangent to the outside is never going to make it to the inside. You get 0.
Wait, what?